Missing data represents a pervasive and often underestimated challenge in nearly every domain of data analysis. Its presence is a common reality, affecting datasets across scientific research, business intelligence, and public policy. Ignoring this issue or mishandling it can severely compromise the integrity of any analytical endeavor. The sources of missing data are remarkably diverse, reflecting the complex processes through which data is collected and recorded. Human error is a frequent contributor, ranging from simple transcription mistakes to incomplete data entry during surveys or experiments. Such errors introduce gaps that are not necessarily systematic. Equipment malfunction also plays a significant role, particularly in automated data collection systems. Sensor failures, network interruptions, or storage device issues can lead to intermittent data loss, creating sporadic missing values. These technical glitches often result in patterns of missingness that are difficult to predict. Participant non-response is another major source, especially prevalent in surveys, clinical trials, and observational studies. Individuals may decline to answer sensitive questions, drop out of a study prematurely, or simply overlook certain items. This type of missingness can be highly informative about the underlying population. The consequences of ignoring or improperly handling missing data are profound and far-reaching. At a fundamental level, it can lead to a distortion of results, presenting a skewed picture of the underlying phenomena. This distortion undermines the reliability of any statistical inference. Furthermore, mishandling missing data often results in biased estimates for parameters of interest. These biases can systematically over- or underestimate true population values, leading to incorrect conclusions about relationships between variables. Such inaccuracies can propagate throughout an analysis. Ultimately, these issues culminate in inaccurate conclusions, which can have serious practical implications. Decisions made based on flawed analyses are inherently risky and can lead to suboptimal outcomes. This is particularly critical in fields where data-driven insights guide strategic choices. Flawed decision-making is the direct downstream effect of compromised data analysis. Whether in business strategy, medical treatment protocols, or public policy formulation, decisions based on unreliable data can incur significant costs, both financial and societal. The integrity of the data directly impacts the quality of the decisions. Therefore, understanding the impact of missing data is not merely a statistical nicety, it is a crucial first step in ensuring the validity and utility of any data-driven project. Recognizing its presence and potential effects is foundational to developing robust and reliable analytical models. This foundational understanding informs every subsequent step in the data preparation and analysis pipeline. The impact of missing data on analytical results hinges critically on the mechanism behind its absence. Not all missing data is created equal. The reason why a data point is missing dictates the appropriate strategies for handling it and the potential biases it might introduce. A clear understanding of these mechanisms is paramount for any data scientist. Statisticians have categorized missing data into three primary mechanisms. These classifications provide a framework for diagnosing the nature of the missingness and for selecting suitable imputation or analysis techniques. Each mechanism carries distinct implications for the validity of statistical inferences. The first category is missing completely at random, or MCAR. This mechanism represents the simplest and least problematic scenario. It implies that the missingness is entirely stochastic and unrelated to any variables in the dataset. The second category is missing at random, or MARCH. This mechanism is more complex, suggesting that the missingness can be explained by other observed variables in the dataset. However, it is not related to the value of the missing data itself, once those observed variables are accounted for. The third and most challenging category is missing not at random, or MNAR. Under this mechanism, the missingness is directly related to the value of the missing data itself, even after accounting for other observed variables. This scenario often introduces significant bias and complexity. Distinguishing between these mechanisms is a critical diagnostic step in any data analysis workflow. Misidentifying the mechanism can lead to the application of inappropriate handling techniques, thereby exacerbating rather than mitigating the problems caused by missing data. Each mechanism demands a tailored approach. Missing completely at random, or MCAR, represents the least problematic mechanism of missing data. In this scenario, the probability of a data point being missing is entirely independent of both observed and unobserved variables in the dataset. It is a truly random event. Specifically, missingness under MCAR is unrelated to any observed variables within the dataset. This means that the characteristics of the individuals or entities with missing values are statistically indistinguishable from those with complete data, based on the information we have. The missingness does not depend on any other recorded attributes. Furthermore, MCAR implies that the missingness is also unrelated to any unobserved variables, including the value of the missing data itself. If a value is missing, its absence provides no information about what that value might have been, nor about any other unmeasured factors. This makes it a purely stochastic event. Consider a practical example, a survey questionnaire where a page is accidentally dropped from a randomly selected subset of completed forms. The missing data on that page is due to a random physical event, not because of any specific characteristics of the respondents or their answers. The missingness is entirely by chance. While MCAR is the most benign form of missingness, it still has consequences. The primary impact of MCAR is a reduction in the overall sample size available for analysis. This reduction can lead to a loss of statistical power, making it harder to detect true effects or relationships. However, a significant advantage of MCAR is that it is less likely to introduce bias into the analysis. Because the missingness is random, the observed data remains a representative sample of the full dataset, albeit a smaller one. Statistical estimates derived from the complete cases are generally unbiased, though less precise. This property makes MCAR a desirable, though often unrealistic, assumption. When MCAR holds, simple methods like listwise deletion, which removes entire rows with any missing values, can yield unbiased parameter estimates. The main trade-off is the loss of efficiency due to reduced sample size. Understanding MCAR is crucial because it sets a baseline for comparison with more complex mechanisms. It highlights that even random missingness has implications for statistical power, even if it preserves the unbiased nature of estimates. This mechanism simplifies the analytical approach considerably. Missing at random, or MAR, describes a more common and complex scenario than MCAR. Under MAR, the probability of a data point being missing is related to other observed data in the dataset. However, it is not related to the value of the missing data itself, once those observed variables are taken into account. This means that while the missingness is systematic, the system is observable within the dataset. We can predict or explain why data is missing by looking at other variables that are present. The missingness is conditional on observed information. For instance, consider a study where older participants are less likely to answer an income question, but their age is recorded. Here, the missingness of income data is related to age, which is an observed variable. If we account for age, the missingness of income is then random. Crucially, MAR implies that if we were to group individuals by their observed characteristics, the missingness within each group would be random. The missingness of income for older individuals is random among older individuals, and similarly for younger individuals. The missingness is not dependent on the actual income value itself. MAR can introduce bias into analysis if not handled appropriately. Simply ignoring MAR data or using naive methods like listwise deletion can lead to biased estimates. This is because the complete cases are no longer a random subset of the full dataset, they are systematically different based on observed characteristics. For example, if older participants are less likely to report income, and older participants also tend to have higher incomes, then listwise deletion would disproportionately remove higher income individuals. This would bias the average income estimate downwards. The observed data is systematically different from the missing data. The key distinction from MCAR is that the missingness is not completely random, it has a pattern that can be explained by other variables we have measured. This systematic difference means that the observed data is not a simple random sample of the population. The distribution of observed values may differ from the distribution of all values, including the missing ones. Therefore, methods that account for the observed relationships causing missingness are necessary for more data. Techniques like multiple imputation or maximum likelihood estimation are designed to leverage the observed data to make valid inferences. These methods aim to correct for the systematic differences introduced by MAR. Understanding MAR is vital because it represents a realistic and frequently encountered scenario in data analysis. Recognizing that missingness is conditional on observed variables guides the selection of more sophisticated and appropriate handling strategies. It moves beyond simple deletion to more robust statistical approaches. Missing not at random, or MNAR, is the most complex and challenging mechanism of missing data. Under MNAR, the probability of a data point being missing is directly related to the value of the missing data itself, even after accounting for all other observed variables. This makes it inherently difficult to address. In MNAR scenarios, the reason a value is missing is precisely because of what that value would have been. The missingness carries intrinsic information about the unobserved data. This self-referential nature of MNAR makes it particularly problematic for statistical inference. Consider a classic example: individuals with high incomes are less likely to report their earnings on a survey. Here, the missingness of the income variable is directly related to the actual income value itself. The higher the income, the greater the probability of it being missing. Another instance might be patients with severe symptoms being more likely to drop out of a clinical trial. The missingness of their later health outcomes is directly tied to the severity of their condition. The missing values are not random, even when considering other observed patient characteristics. MNAR can severely bias results if not properly addressed, often leading to incorrect conclusions. Standard methods that assume MCAR or MAR will produce biased estimates because they fail to account for the systematic relationship between the missingness and the unobserved value. The observed data is fundamentally different from the missing data in a way that cannot be explained by other variables. The missing values are systematically different from the observed values in a way that is unobservable. This inherent unobservability is what makes MNAR so challenging. We cannot simply look at other variables to explain the missingness, because the explanation lies within the missing value itself. Furthermore, the relationship causing missingness in MNAR situations is often unknown and unquantifiable. Without external information or strong theoretical assumptions, it is impossible to definitively model this relationship using only the available data. This lack of information complicates the development of appropriate imputation or analysis strategies. Addressing MNAR typically requires making strong, untestable assumptions about the missing data mechanism. Sensitivity analyses, where different plausible MNAR mechanisms are assumed and tested, are often employed to assess the robustness of conclusions. These methods attempt to model the unobservable relationship. Understanding MNAR is critical because it highlights the limitations of standard missing data techniques. It forces data scientists to consider the underlying reasons for missingness more deeply and to acknowledge the potential for uncorrectable biases. This mechanism underscores the importance of careful study design and data collection to minimize its occurrence. The impact of ignoring missing data varies significantly depending on the underlying mechanism and the specific analytical method employed. Different naive approaches to handling missingness can introduce distinct types of biases and inefficiencies. Understanding these specific consequences is crucial for informed decision-making. One of the most common and seemingly straightforward approaches is listwise deletion, also known as complete case analysis. This method involves removing any entire row or observation that contains even a single missing value. While simple to implement, its consequences can be severe. Listwise deletion invariably leads to a reduced statistical power. By discarding observations, the effective sample size shrinks, making it harder to detect statistically significant effects. This reduction in power increases the risk of type 2 errors, where true effects are missed. More critically, listwise deletion can result in biased estimates, especially when the data is MAR or MNAR. If the missingness is systematic, removing incomplete cases distorts the sample, making the remaining complete cases unrepresentative of the original population. This bias can lead to incorrect conclusions about population parameters. For instance, if missingness is related to an outcome variable, listwise deletion will systematically alter the distribution of that outcome. Another common naive approach is mean imputation, where missing values are replaced with the mean of the observed values for that variable. While it preserves the sample size, mean imputation introduces its own set of problems. Mean imputation can significantly underestimate the variance of the imputed variable. By replacing missing values with a single, central value, it reduces the spread of the data. This artificial reduction in variance can lead to narrower confidence intervals and inflated test statistics, giving a false sense of precision. Furthermore, mean imputation can distort the relationships between variables. Replacing missing values with the mean weakens the correlations between the imputed variable and other variables in the dataset. This attenuation of relationships can obscure true associations and lead to incorrect conclusions about multivariate models. It essentially treats imputed values as certain, rather than uncertain. Both listwise deletion and mean imputation, while simple, demonstrate how ignoring the underlying missing data mechanism can lead to compromised analytical results. They highlight the necessity of employing more sophisticated methods that account for the nature of missingness. The choice of handling method directly impacts the validity of the analysis. The consequences of improperly handling missing data extend far beyond mere statistical accuracy. They permeate various domains, influencing the quality of decisions and the validity of conclusions drawn from data. The integrity of data analysis is foundational to reliable outcomes in many fields. In the business world, ignoring missing data can lead to poor business decisions. Inaccurate market segmentation, flawed customer behavior predictions, or misjudged financial forecasts can result from analyses built on compromised data. These errors can translate into significant financial losses or missed opportunities. Similarly, in scientific research, mishandling missing data can result in flawed scientific conclusions. This undermines the credibility of studies, impedes scientific progress, and can lead to misdirection in future research efforts. The reproducibility and reliability of scientific findings are directly at stake. For public policy, the implications are equally severe, leading to ineffective policy implementations. Policies designed based on biased data might fail to address the intended problems or, worse, exacerbate existing issues. This can have detrimental effects on public welfare and resource allocation. Consider real-world examples of this impact. In healthcare, missing patient data can lead to misdiagnosis or inappropriate treatment plans. If crucial symptoms or medical history are missing, clinicians might make suboptimal decisions, potentially harming patient outcomes. The absence of data can be as critical as incorrect data. In market research, missing consumer data can result in inaccurate targeting and ineffective marketing campaigns. If demographic or behavioral data is incomplete, companies might misidentify their target audience or develop products that do not resonate with actual consumer needs. This wastes resources and diminishes market effectiveness. Therefore, a thorough understanding of the missing data mechanism and its potential impact is absolutely essential for any data professional. This understanding forms the basis for selecting appropriate and robust methods to address the problem. It is a prerequisite for sound analytical practice. This comprehensive understanding guides the selection of appropriate handling techniques, moving beyond naive approaches to more sophisticated imputation or modeling strategies. The chosen method must align with the identified missing data mechanism to ensure validity. Ultimately, this diligence ensures the integrity and reliability of the analysis. By properly addressing missing data, data scientists can produce results that are trustworthy and defensible. This builds confidence in the analytical process and its outputs. Furthermore, it ensures the validity of conclusions drawn from the data. Reliable conclusions are the bedrock of evidence-based decision-making, whether in research, business, or policy. The effort invested in handling missing data correctly pays dividends in the quality of insights generated. This foundational knowledge paves the way for exploring various advanced methods for addressing missing data, such as multiple imputation, maximum likelihood estimation, or specialized modeling techniques. It empowers data scientists to choose the most effective strategy for their specific context, moving from problem identification to robust solution implementation.